So yeah, I'm Lydia. I'm from Portugal, but I'm currently in the UK, in Lancaster, doing my PhD. Can you hear me fine? Okay. Um, so my talk is about the joint modeling of the bulk and tail of bivariate data, and I'm supervised by Jennifer Wadsworth in Lancaster and Adrian Onhagen in Dublin. Um, just, sorry. Just a little bit of motivation. So sometimes we are not just interested in modeling the extremes of the data, but also the rest of the observations. So what we say, what we call the bulk of the distribution. And this might be important in environmental applications or in financial data as well. So here I just have a scatter plot of the data I use for the case study of this paper. I will come back to it later, but it's just to show that sometimes the not extremes, but values that are concerning are in the body of the distribution here above the line 100. Oops. Okay. So this has been done in the univariate framework. There have been proposed some methods, some parametric, semi-parametric, and non-parametric models. And usually what is behind these methods is fitting a generalized Pareto distribution to the tail. This is known to be a suitable distribution for extreme observations. And then the body is either estimated non-parametrically, as in the right figure, so empirically, or in the left figure, they decided to fit the bulk of the distribution with a gamma distribution. So they define a different distribution for the non-extreme observations. And in the middle one, they fit two distributions, a GPD and a variable to the whole data. And then by means of a mixed weighting function, they obtain a mixture modeling. In the majority of these cases, a threshold has to be defined. And above this threshold, the GPD is fitted. But in the middle one, this threshold is estimated implicitly, so we don't have to define it beforehand. But when we move to the multivariate case, this has not been done as much in the literature. So in a multivariate setting, we are also concerned about the dependence between variables, and this becomes a problem. So I'm just here introducing what a copula is. And a copula is a joint distribution of a random vector x1 to xd, and given by this equation down. So we have the joint distribution defined by the copula, and then we just need the marginals of each variable. And in the pictures, what I'm showing is usual measures as the tau, the concordance Kendall's tau, or the Pearson correlation coefficient. They give an idea of the correlation, the overall correlation, but not how that the dependence involves all the support. So here we can see with the copula, giving the same value of the Kendall's tau, we have different structures of dependence. So if we have a Gaussian, this is more or less uniform in the support in the 0, 1 to the square. But if we have a Joe copula, we can see that is more dependent in the extremes rather than in the body. So that's what I'm trying to show, that the copulas are able to capture a dependence differently than the overall dependence measures that we are used to. So coming back to the problem, as I said before, there are not many available methods in the literature that capture the body and the tail of a distribution, multivariate distribution. But one of the ones available is this one, Double et al. So they model the full data set by fitting one copula to the body, here represented in blue, and one copula to the tail, represented in red. As we can see in this figure, I did it on purpose. It doesn't offer a smooth transition between the two copulas. We defined two thresholds, one at 0.8 and one at 0.5. And then above these thresholds, we fitted the copula to the tail. And we can see at the limit of these thresholds, the value of the thresholds, there is a clear step between the two copulas. So it requires the choice of thresholds, as I said. And in the paper, they don't they don't perform an inference because the likelihood of the model doesn't have a closed form. So what we propose, we follow up on that model And we also define a density C star in the unit square. So we have variables U star, V star in the unit square, and we define the density as follows. So we have a pi function, a CT function, and a CB function. So we have two copular densities, CT and CB. And CT we call the copula tailored to the tail, so the copula that we want to be dominant in the tail, and CB we call the body copula, which is the one that we want to be dominant in the body. And then we have pi function, a pi function that is a dynamic weighting function. It's again defined in the unit square, and we want it to be increasing in U star and V star. And this is because if pi is close to 1, then C star here will be more, it will have more influence in the distribution. And at the same time, this part here, 1 minus pi star, will be close to 0, so CB won't have much of an influence. But if for smaller values of pi, the opposite is true, so we have 1 minus pi to be close to 1, so CB will have more influence, and pi will be close to 0, so CST won't have much of an influence. And then we have a gamma to be the vector of model parameters and kappa to be the normalizing constant. So this is our density. And here are two different examples of this model with different weighting functions. Both are increasing in U star and V star. And we can see that there is a difference depending on the weighting function. There is more of an influence of one of the copulas. So for the left-hand side, we have more influence of the body copula, and on the right-hand side of the tail copula, but you can see that we have points of each copula along the unit square in both cases. So our model doesn't require choice of threshold. So this is quite a good thing because it's a big problem in extreme value theory. Framework is that we have to choose a threshold, and sometimes a bad threshold doesn't hold for suitable distributions on the tail. So it has to be, the choice has to be careful, and because we don't require that, it's a positive point. We also offer a smooth transition between the body and tail copulas. We can see that with, as I showed before, the points being spread out along the unit square. But as the Albach et al., it's also hard to perform inference on it because we don't know the true marginals. So we overcome that by fitting the copula of the density C star via numerical integration. And this is done as follows. This is the more technical slide, and I'm going to skip it, but it's just to show how we fitted the copula density of C star. We are also interested in checking the extremal behavior of the variables and the properties of the model. This was introduced yesterday in the last talk of the day, but we are interested in checking if the extreme values are likable to occur together. So if we have asymptotic dependence, or if they are not likable, at least two or more are not likely to occur together, to be extreme together. So we have asymptotic independence. And we use two measures to model this. So we have the chi, which is the tail dependence coefficient, and this is the limit of the probability of one variable being larger than some threshold R, given that the other variable is larger than that threshold R. And then this is the limit of this probability when R tends to 1. This is just for the bivariate case. It can be extended to more than 2 dimensions. And then we use the eta coefficient. This is the residual tail dependence coefficient, and it measures the decay of the probability, the above probability, basically. And so we have asymptotic dependence if chi is positive and it is equal to 1, and asymptotic independence if chi is equal to 0 and eta is different than 1. We managed to get some theoretical properties of this model for some cases, not all of them. And we arrived to some conclusions. So depending on the weighting function used, the copula tailored to the body has some influence in chi in some of the cases. So if the pi function is the product of the variables power to some parameter theta that is positive, and the copula tailored to the tail is asymptotic dependent, then the chi of our model is dominated by the chi of the tail copula, but has an influence of the chi of the body copula. But if we have the same weighting function, but the tail copula is asymptotic independent, then the chi of our model is the same from the chi of the tail copula. And the same happens if we move to the other weighting function that we considered in the paper. The chi will be the one from the copulator to the tail, independently of the nature of this copula. So for one particular case, if we derive the exact form. So if we have the copulator to the body to be frank, and this is known to be asymptotic independent. So down here in the brackets, I have the values of the chi's and etas for each one of the copulas. So we have chi equal to 0 and eta equal to 0.5 for the frank copula with parameter beta. And then we have a Gumbo copula, which is asymptotic dependent with the chi t, this one down here. For the tail copula then, and this pi function here, the product of the variables power to theta, then the chi of our model is this one, this big expression. And then we have, of course, theta equal to 1. But if we move to the other weighting function that we consider, then the chi of our model is the sum of chi t. And this is also shown in these pictures. So we have the product of the variables in the left plot and the other weighting function in the right plot. And we can see that the chi of our model, the limiting value of the chi of our model is the one in pink. And the chi for different values of thresholds are for the model is given in this blue line. So it's decaying to the value that we derived in the pink line. And the same on the right-hand side. And we can see it's the same. We have the chi t to be the same as chi model, and they both go down. We also checked for different values of theta, and theta is the parameter of the weighting function. What happened to the chi of the model for different values of theta and for different values of thresholds. And we can see on the left-hand side that there is an influence of the body as I said before. And this influence of the body is bigger if theta is bigger. So if theta is bigger in this copula, then there is a preference for CB because pi is close to 0. And if I think it's smaller than 2, then we have pi to be bigger than 1, not 1, sorry, pi close to 1. And the same happens in the eta plot. Here is the other weighting function, and the same happens. We then did a simulation study to check if the model worked correctly. The first simulation that we did was to check if the inference was working. So we estimated the parameters via maximum likelihood estimation. And we have this simulation setup. So we have the tail copula to be a Gaussian with a raw parameter of 0.6. The body copula to be a jaw with alpha equal to 2. And then we have the product as the weighting function with theta equal to 1. And we did that for 2 different sample sizes, and we repeated 100 times. And here are the results. We can see it's doing pretty well. The red line is the true value. And when we increase the sample size, we get less variability, which is nice. We then checked what happened if we misspecified the model. So the first misspecification that we considered was having a true data coming from a copula and having that copula as a true component, as a component of the weighting copula model. So we have the true data coming from a jaw with an alpha equal to 2, and we have this copula to be the one tailored to the body, and then CT to be a Clayton copula. Again, the same weighting function and 1,000 data points. We can see that we just have a true value for jaw because it's the only one that we know. The data came from the jaw copula, and we can see that there is a little bit of bias, but it's not that bad. But when we move to the Clayton parameter, this is completely, it's going from 0 to 15. And this makes sense because it's not we don't have data coming from this copula, so less points from this copula are coming, which makes sense. And the same we can see on the theta parameter. So the theta here is in the log scale to be for visualization, but we can see it's very big, and it's giving preference to the body copula, which is the jaw, which is the true data. So it's working quite well if we misspecify in this sense. And then here we have just the comparison of AICs, and just, I think 5 times it shows the weighted copula model over the single copula, which is quite good. We also consider a different case of misspecification, so having true data coming from a copula, but not having this copula as one of the components. So we have the data coming from a Gaussian copula with this parameter, rho, 0.65, and we consider 4 different models. These ones here that I listed here, and according to the best average IC, the model that was fitted the best was the third model, so having the copula tailored to the tail being an inverted gumball and the copula tailored to the body being a student T copula. We have the same weighting function, 1,000 data points, and we fitted each model 50 times. So picking up on the third model, we decided to compare with the extremal dependence of the Gaussian to see if the dependence structure was captured correctly, even if we misspecified the model. And here is the comparison. So the red dots are the eta values at each threshold, ranging from 0.65 to 0.99 for the Gaussian. And we can see the etas of the third model. It's bigger on the bigger threshold because there is less data as well. But it captures quite well the dependence, even though we didn't consider a true dependence, which was a Gaussian. So we were quite happy with these results. And then we applied this to a case study. We were interested in seeing the relationship between ozone and temperature data. So the temperature may influence the levels of ozone concentration in the air. So that's why we decided to compare these two. And here in the table, I have the legal thresholds for ozone levels in the UK. And we have the low to be until 100, the moderate to be above 100, high, and there is a very high. So sometimes the legal thresholds may be found in the body, not just in the tails. And we applied the model to the summers between 2011 and 2019 of Blackpool in the UK. This is in the north of England. So here on the left side, we have the same scatter plot as the first slide that I showed in the original scale. So we have on the y-axis the ozone, and then on the temperature is on the x-axis, and then the legal thresholds are in the lines, the colored lines. On the right-hand side, we have the same variables, but transformed to uniform so that we are able to see the dependence and how that varies in the unit square. And we can see that there seems to be a negative correlation in the body, but there seems to be positive association in the tail. So we were hoping that our model was able to capture this. But we started by fitting just a single copula to the whole data, and these were the copulas that we considered. I didn't show the parameter estimates here, but the only copulas that are able to capture negative dependence are the Gaussian, the Frank, and the student T. And none of these three had negative parameters, so they were not able to capture this negative correlation that we seem to see on the scatter plot before. And according to the AIC, the best fitting copula was the Joe. And here on the right-hand side, we have a plot of the etas alongside the whole distribution, so from 0 to 1. And on the black line, we have the empirical values. And then on the colored lines, we have the etas for each one of the couples we fitted. And I know that the colors they seem the same, but the best one in the tail seems to be the Joe, is this orange here that increases as the empirical values increase. But none of them capture really well the body or the tail even. So we fitted the weighted copula model. We first fitted with this product between the variables power to theta, and we fitted to a lot of combinations of copulas, but here I'm just showing the best 5 models in terms of AIC. And in the body copula, we can see that the selected one was either Gaussian or Frank. As I said before, this is able to capture the negative correlation, and we can see that they capture the negative correlation here on the estimates of beta. They are all negative. And then the copula tailored to the tail were these 4 ones, And these are known to be asymptotic dependent, so able to capture the positive dependence in the extremes. So we were quite happy that, yeah. And on the estimates for T2, we can see they are all smaller than 1, so more there is a preference over of CT over CB, so there are more points coming from an asymptotic dependent copula. We plotted again the eta plot for the thresholds going from 0 to 1, and we can see that the fit in the body, and compared with the empirical, the fit in the body had an improvement, a clear improvement, so they seem to be doing better, and this is because the negative correlation is mirrored, but the fit in the tail is still poor, and the best one is the one, model 5, which is the one that has the Joe couple as a component. We fitted again the weighting couple model for a different weighting function, and we get again the same 5 models as the best AIC. The AIC compared to the last ones have an improvement even, because the last ones were in this range, and these ones are in the 200. We have the same body copulas, so the negative correlation is mirrored, is bigger even than before, and we have the same tail copulas. And this theta for this weighting function still gives preference to CT over CB. And the eta plot is way better. So there is a good fit in the body and a way better fit in the tail. And between these 5 models, there is not one that would represent this eta bad. So we were quite happy about that. We also computed some other diagnostics. So we have the Kendall's law, so the overall correlation of the data, and compared with the empirical and the 95% confidence interval. And we can see that all the 5 models, these are the 5 models with the second weighting function. All the 5 models are within the confidence interval. We then computed the probability of a temperature being high. 24 is high for Blackpool. So they barely reach 24 in summer. So we computed the probability of the temperature being high, so bigger than 24, and the ozone exceeding the moderate threshold. And again, compared with the empirical and the 95% confidence intervals. And again, they are within the confidence interval. And we also computed the probability of exceeding this moderate threshold, given that the temperature is within a range of values here, 22 and 23. And again, compared with the empirical, and they are within the 95% confidence interval. So we were quite happy with that. So as a conclusion, the model provides a better fit than just fitting a single copula to the data, and it's flexible. So we showed that it's able to capture different structures within the same data set. But it is computationally expensive. We are in the bivariate set, and for the sample size of 1,000, it took more than an hour to compute each one of the likelihoods. So it's quite expensive, and we are assuming stationarity, which is not true for most of the real case or real data. So we should account for non-stationarity and include covariates in the model. And that's it. Thank you for listening. And these are the references that I referenced in the talk.
For your presentation. You have used some of your time for questions, so if there are any questions from audience, maybe we can manage to do 1 or 2, but rest of them would have to be postponed to the breakout rooms. So Zikica Lukic has a question, is that right?
Yes, I'm audible.
Yeah.
Okay, great. This might be a naive question, but you have mentioned that you have worked on bivariate data.
Yeah.
What would happen if the dimension would increase? For example, if we would consider the dimension 5 instead of 2?
Yeah, so it's infeasible. Well, if we have a good computational power, would be feasible, but because we have these integrations here, in a 5-dimensional case, we would have a 5 integrals, and it would be very computational. Well, it would be a lot.
Yeah, and how do you compute these integrals? What is the notation?
Sorry?
where does the limitation comes from? You know, why
Oh,
is it so?
because it's approximations and it just computes at every point and just takes time to invert. Because we have to invert, we have to compute these integrals, we have to compute another integral, so it can, and yeah, it becomes expensive.